Hello and welcome. The data just dropped, and it's not what anyone expected. Right now, as you watch this, an object from another star system is tearing through our cosmic backyard at 200,000 kilometers per hour. We've thrown our most powerful instruments at it. We've listened with ears sensitive enough to hear a cell phone whisper from millions of kilometers away. And what we found, or rather, what we didn't find, has split the scientific community down the middle. Tonight, we're diving into the fresh analysis of 3I Atlas. Because the numbers are in, the observations are complete, and I need to show you why this simple answer is anything but simple. Let's look closer at the data. This isn't just another rock. 3I Atlas is only the third confirmed object in history known to have entered our solar system from interstellar space. Think about that for a moment. For centuries, we stared up at the dome of the night sky, assuming that everything moving through the dark was part of our own family. Comets, asteroids, planets bound to our sun. Then came Oumuamua, then Borisov, and now 3I Atlas. 3 visitors in less than a decade. It forces us to ask, is the traffic increasing, or are we just finally opening our eyes? The object is moving fast, incredibly fast. We are tracking speeds on the order of 200,000 kilometers per hour relative to the Sun. To put that in perspective, that is fast enough to travel from Earth to the Moon in under 2 hours. At that velocity, the Sun's gravity is just a speed bump. It isn't being captured. It isn't staying. It is a drive-by. And that speed is exactly why we are in such a rush. The window for observation wasn't measured in years or months, but in weeks. And that window is closing right now. Before we dive into the new analysis, and specifically the controversial radio data that has just been released, if you want to stay on the cutting edge of this investigation as we parse the incoming stream from our observatories, make sure you hit that subscribe button. We are going to be following 3I Atlas until it fades from our most powerful sensors, and you won't want to miss what comes next. Now, back to the trajectory. When we plot the path of 3I Atlas, we see it diving steeply into the inner solar system, swinging past the Sun and shooting back out. It's a hyperbolic trajectory, the mathematical signature of an interstellar origin. But unlike Oumuamua, which tumbled and accelerated in ways that baffled physicists, 3I Atlas appears, at least optically, to be behaving normally, or so it seemed. The initial optical and infrared measurements painted a picture of a standard cometary body. We have nucleus size estimates ranging from hundreds of meters to perhaps several kilometers. It's a wide margin of error, I know, but that reflects the inherent difficulty of observing a fast-moving target that is already receding. It's like trying to measure the size of a bullet while it's flying away from you. We see a coma, we see a tail, classic signs of outgassing, of ice sublimating into space as the object heats up. But here is where the narrative shifts, because while the optical telescopes were counting photons, a different kind of ear was turning toward the sky. A much larger ear. The scientific community realized that if this object were anything other than a frozen chunk of rock and ice, if there was even a 1,000,000,000 to 1 chance it was an artificial probe, a derelict craft, or something we don't yet have a name for, we needed to listen. We needed to listen right now, at the point of closest approach. The logic is sound. If you were a traveler passing through a foreign system and you were active, you might communicate, or you might leak radiation, or you might use radar to scan your surroundings. Optical telescopes see reflected sunlight. Radio telescopes see activity. They see energy. So, the decision was made. The Breakthrough Listen program, the most comprehensive search for extraterrestrial intelligence, SETI in history, requisitioned time on one of the most sensitive instruments on Earth. They weren't just going to look at it. They were going to scan it with unprecedented intensity. The target date was set for December 18, 2025. This was the critical moment. The geometry was optimal. The distance was minimized. If 3i Atlas had anything to say, this was the moment we would hear it. The anticipation in the control rooms was palpable. We weren't just looking for a comet. We were looking for a techno-signature, a sign that we are not alone. But as we prepare to examine the results of that scan, we have to understand the stakes. A positive result would change human history instantly. A negative result? Well, a negative result is where the real science begins, because silence in radio astronomy is never just silence. It is a data point. It defines the limits of what is out there. And as we are about to see, the silence of 3i Atlas is loud. The object passed through the inner regions of our system under the gaze of our most advanced technology. We threw everything we had at it in the radio spectrum, and what we found, or rather, what we didn't find, has triggered a fierce debate about assumptions, methodology, and the very nature of how we search for life in the cosmos. We need to move from the optical tracking to the radio spectrum. We need to go to West Virginia, to the shadow of a massive dish, to understand exactly what happened on December 18th. Because the data that came back is not as unambiguous as it might seem at first glance. The headline says, "No signal." But the data? The data whispers something else entirely. It whispers about the limits of our own perception. Let's go to Green Bank. We are standing, metaphorically, in the quiet zone of West Virginia. Here, nestled in the mountains, shielded from the radio interference of the modern world, sits the Robert C. Byrd Green Bank Telescope. It is a marvel of engineering, a dish 100 meters across. That is larger than a football field. It is the largest fully steerable radio telescope on the planet. And on December 18th, 2025, this massive ear was turned directly toward 3i Atlas. This wasn't a casual glance. This was a targeted, high-intensity interrogation of the interstellar visitor. The Breakthrough Listen program, which has been scanning the stars for signs of intelligent life for a decade, dedicated this precious telescope time specifically because of the object's proximity. The timing was calculated to coincide with the comet's closest approach to Earth. If there was ever a time to catch a whisper from this object, this was it. Let's break down exactly what they did, because the methodology matters. You can't just listen to the universe. You have to choose a frequency. You have to tune your radio. The team at Green Bank scanned the frequency range from 1 to 12 gigahertz. Why this range? This is the water hole and beyond, a quiet part of the radio spectrum where background noise from the galaxy is relatively low and where our atmosphere is transparent. It is the classic frequency band where radio astronomers assume a technological civilization might transmit. It covers everything from our own Wi-Fi and satellite communications to the frequencies used by deep space radar. By scanning from 1 to 12 gigahertz, they were effectively checking billions of channels simultaneously, looking for anything that stood out against the cosmic static. Here is the crucial detail. They weren't just looking for a broadcast, they were looking for narrowband signals. Nature, generally speaking, is broadband. When a star explodes, or a black hole eats gas, or a quasar fires a jet, it screams across the radio spectrum. It's messy, it's loud, it's everywhere at once. Technology is different. Technology is precise. When we send a signal, we compress the energy into a very narrow frequency to save power and carry information. A narrowband signal is the hallmark of engineering. It is the fingerprint of intelligence. So, on December 18th, the Green Bank telescope tracked 3I Atlas as it raced across the sky. The dish moved silently, compensating for the rotation of the Earth and the rapid motion of the comet itself. The receivers were cooling to near absolute zero to minimize their own electronic noise. The supercomputers in the back end were crunching petabytes of raw voltage data, performing Fourier transforms in real time, breaking the radio waves down into their component frequencies. They were looking for a spike, a single, sharp line on the graph that shouldn't be there, a tone, a beep, a sequence. Anything that looked like it was manufactured. The sensitivity of this observation was staggering. The authors of the study emphasized that the observations would have allowed the detection of persistent signals down to power levels on the order of 100 milliwatts. Let's pause on that number, 100 milliwatts. That is roughly the power of a standard smartphone trying to connect to a cell tower. Imagine a smartphone floating in the void of space, millions of kilometers away, transmitting back to Earth. The Green Bank telescope could have seen it. That is the level of precision we are dealing with. We aren't talking about needing a Death Star super laser to be detected. We are talking about consumer electronics. If 3I Atlas had a radio transmitter on board, and if that transmitter was omnidirectional, sending waves out in all directions like a light bulb, and if it was transmitting in the 1 to 12 gigahertz range with the power of a mere cell phone, we should have seen it. The graph should have spiked. The alarm should have rung. The team observed. They recorded. They processed. They filtered out the interference from our own satellites, which is a huge problem in radio astronomy, distinguishing us from them. They looked for Doppler drifts, the slight shift in frequency caused by the object moving relative to the telescope, a telltale sign that the signal is coming from the target and not from a tower on a nearby mountain. They did all of this, and then they published the preprint. The result was a flat line. No candidate technosignatures were detected, no narrowband transmissions, no beacons, no telemetry, nothing. In the scientific paper, this is presented as a strong negative result, and formally it is. It puts a hard upper limit on the radio brightness of the object. We can now say with high confidence that on December 18th, 3I Atlas was not emitting a continuous radio beacon in the L, S, C, or X bands above 100 milliwatts. But this is where the science gets interesting, because a negative result is not the same as proof of non-existence. It is proof of non-detection under specific conditions. We have established the capability. We could hear a whisper. We have established the result. We heard silence. But what does that silence actually mean? Does it mean the object is natural? Or does it mean we were listening for the wrong thing? To understand the implications, we have to look at what wasn't measured. We have to look at the shadows in the data. Because while the Green Bank telescope is a masterpiece of technology, it is not all-seeing, and 3i Atlas is a master of evasion. As we move to analyze the signal that wasn't, keep in mind that 100 milliwatt figure. It sounds impressive. It is impressive, but it relies on assumptions. And in the hunt for extraterrestrial intelligence, assumptions are the most dangerous things we have. Let's analyze the silence. The silence from 3i Atlas is deafening. We have a 100-meter ear turned to the sky, capable of detecting a cell phone's worth of energy across the void, and it hears nothing. The Breakthrough Listen team has delivered their verdict: no technosignatures. This contradicts what we previously thought, or perhaps what many hoped. When an interstellar object enters our system, the imagination naturally runs wild. We think of Arthur C. Clarke's Rendezvous with Rama. We think of probes waking up as they approach a star. We hope for a hello. But the data from December 18th is cold, hard, and empty. Let's unpack this strong negative result. In science, a negative result is incredibly valuable. It clears the board. It tells us where not to look, or at least what isn't happening. We now know that 3i Atlas is not a loud, broadcasting beacon. It is not screaming its presence to the galaxy. If it were a derelict spacecraft with a functioning emergency transponder operating in our standard communication frequencies, we likely would have caught it. The 100 milliwatt sensitivity is the headline number here. It rules out a specific class of loud artificial objects. It means that if this were a piece of technology, it isn't behaving like our technology would. When we send probes like Voyager or New Horizons into the dark, they constantly phone home. They have high-gain antennas pointed at Earth, blasting data back to the deep space network. 3i Atlas is doing none of that. But before we close the book and label it a rock, we have to ask, is this silence absolute? This brings us to the midpoint of our investigation, and I want to hear from you. Do you think a negative radio search is enough to prove an object is natural? Or could a technological object simply be quiet? Leave your thoughts in the comments below. I read them, and the best theories might make it into a follow-up. Now, back to the analysis. The paper states that the sensitivity would have allowed detection. That is the key phrase. It assumes a continuous signal. It assumes the signal was on during the observation window. But radio searches, by definition, are snapshots in time. Imagine you are trying to determine if a house is inhabited. You walk by the window for 5 minutes on a Tuesday afternoon. You don't see anyone. You don't hear music. You don't see the TV on. Do you conclude the house is empty? Or do you conclude that at that specific moment, the occupants were quiet or in another room or asleep? The Green Bank observation was a snapshot, a very high-resolution snapshot, but a snapshot nonetheless. 3I Atlas was moving. The telescope was tracking. The observation lasted for a specific duration. If the object transmits in bursts, say a millisecond ping every hour, the chance of catching it during a scan is statistically low. Furthermore, the search looked for narrowband signals. This is the gold standard for SETI, as we discussed, because nature doesn't do narrowband. But who is to say an advanced civilization uses narrowband radio for communication? Maybe they use broadband spread spectrum signals, which look like noise to the uninitiated. Our own military communications often use spread spectrum to avoid detection and jamming. If you look at a spread spectrum signal with a standard radio receiver, it just looks like static. You need the key to decode it. We don't have the key for 3I Atlas. And then there is the frequency range, 1 to 12 gigahertz. It's a huge slice of the pie, but it's not the whole pie. We didn't look in the optical bands for laser communication, though other optical telescopes were watching. They weren't looking for nanosecond laser pulses. We didn't look in the lower frequencies or the higher millimeter waves. So, the strong negative result is actually a very specific statement. We found no continuous, narrowband radio signals between 1 and 12 gigahertz on December 18th. That is a mouthful, but it is the scientific truth. It is not, there are no aliens. It is, there is no radio noise in this specific room at this specific time. This distinction is vital. The public sphere often conflates evidence of absence with absence of evidence. We have an absence of evidence for radio transmissions. That is a fact. But inherent limitations in the methodology prevent this no from being interpreted as universal. We are left with a puzzle. The object looks like a comet. It acts like a comet. It is silent like a comet. Occam's razor, the principle that the simplest explanation is usually the correct one, screams that it is a comet, and yet the very nature of its origin keeps the door slightly ajar. If it were artificial, why would it be silent? Is it broken? Is it a passive probe? Or is it simply ignoring us? These are the questions that arise when you stare at a null result. The data is clean, but the interpretation is messy. And, as we are about to see, there are scenarios, hypothetical, yes, but physically possible, where an object could be artificial and yet remain completely invisible to the Green Bank telescope. We need to explore the shadows in the data. We need to look at what we might have missed, because in the game of interstellar hide-and-seek, the seeker has to be lucky every time. The hider only has to be lucky once. Let's look at the scenarios where the silence makes sense. We have established that 3I Atlas is silent, but silence is a tricky thing. In the context of an interstellar encounter, silence can be a strategy, a malfunction, or simply a lack of intent. The no from Green Bank is definitive for the data collected, but it is not a universal no. So, what does this actually mean? It means we have to speculate. We have to step cautiously outside the bounds of rigorous science and into the realm of hypothesis, not to invent fantasies, but to stress test our search methods. If 3I Atlas were artificial, how could it evade our best ears? The first scenario is the directed beam hypothesis. The Green Bank search assumes an omnidirectional signal, a broadcast going out in all directions. But if you are an advanced probe, why waste energy shouting at the void? You would use a tight beam. You would aim your transmitter directly at your home star or at a relay station. If Earth doesn't happen to be in that line of sight, and the odds are astronomical that we wouldn't be, we would hear nothing. We could be staring right at a functioning transmitter, but if the beam is pointed away from us, it's invisible. It's like trying to see a flashlight beam from the side. Unless there's dust or fog to scatter the light, you don't see it. The second scenario is radio silence. This is the idea that the object is deliberately maintaining silence while passing through a region under intense scrutiny. This sounds paranoid. I know. It implies intent. It implies that the object knows we are here and knows we are listening. But consider our own submarines. They run silent when they are in hostile or unknown waters. If 3i Atlas is a surveillance probe, its primary mission would be to gather data, not to transmit it immediately. It might store the data and wait until it is back in deep space to burst transmit it home. In this scenario, our silence is exactly what we should expect. The third scenario is exotic comms. We are listening for radio waves because we use radio waves, but radio might be the smoke signals of the galaxy, primitive, slow, and inefficient. An advanced civilization might use neutrino beams, gravitational waves, or quantum entanglement for communication, channels that modern astronomy simply does not monitor for messages. We are looking for a message in a bottle, while they might be using the galactic internet. These ideas lack direct evidence. I want to be very clear about that. There is zero proof for any of this, but they highlight an important point. A null result in the radio domain always describes the limits of our search, not the totality of reality. The public speculation reflects this gap. People are asking, does the absence of a signal mean it's a rock? The answer is, probably, but not definitely. And then there is the space junk theory. What if it is artificial, but dead? A piece of debris from a long-dead civilization, a spent rocket stage, a fragment of a Dyson sphere. It wouldn't transmit. It would just tumble through the dark, silent, and cold. In that case, radio searches would never find it. We would need to rely entirely on physical characteristics, shape, rotation, composition. This brings us back to the hard data we do have. The radio search was a shot in the dark, a necessary one, but a long shot. The real story of 3i Atlas is written in its motion, its reflection of sunlight, and its interaction with the solar wind. While we were listening for a beep, NASA was measuring the physical reality of the object, and those measurements paint a picture that is less science fiction and more planetary science. But even there, the picture is not fully resolved. The object passed us at a distance of about 1.8 astronomical units. That's nearly twice the distance from Earth to the Sun. It didn't skim the atmosphere. It stayed out in the asteroid belt. That distance makes optical resolution difficult. We see a point of light, not a resolved disk. We infer size from brightness. The estimates range from hundreds of meters to kilometers. That is a huge range. It's the difference between a skyscraper and a city. And the surface composition? We think it's ice and dust because it developed a tail. But the composition of that tail, the specific chemical fingerprint, is still being analyzed from the spectra. So we have a silent object, a fast object, an object that looks like a comet but comes from the stars. The radio silence is a piece of the puzzle, a dark tile in a mosaic that is still being assembled. As 3I Atlas speeds away, heading back into the interstellar night, we are left with the final trajectory. The physical path it took, and the scientific path we must now follow to understand it. The excitement of the alien signal has faded, replaced by the rigorous, slow work of analyzing the optical data. We are learning that the galaxy is not empty. It is full of debris, full of wanderers. Oumuamua showed us that interstellar objects can be strange. Borisov showed us they can be familiar. 3I Atlas shows us they can be elusive. Each of these visitors teaches us something new about our place in the cosmos. They teach us that the solar system is not a walled garden. We are part of a galactic ecosystem. Material flows in, material flows out. The investigation into 3I Atlas is winding down, but the search is just beginning. The Breakthrough Listen program continues. The Vera Rubin Observatory is coming online, promising to find not just 3, but potentially hundreds of these interstellar objects in the coming years. We are moving from the era of anecdotal discovery to the era of statistical population studies. Next time, we might catch one earlier. We might have time to send a probe to intercept it. We might be able to touch it, to drill into it, to see for ourselves what lies beneath the crust. Until then, 3I Atlas remains a data point, a silent, speeding enigma. It is a reminder that the universe is vast, mostly quiet, and full of mysteries waiting for the right moment and the right frequency to be revealed. If you enjoyed this deep dive into the science of the unknown, please hit that like button. It helps the algorithm know that you want more content that respects your intelligence and digs into the real data. We will keep watching the skies, because if 3I Atlas taught us anything, it's that you never know who or what is just passing through. But the story isn't over. The silence itself is a finding. And as we combine the radio null result with the NASA tracking data, a final, conservative, yet fascinating picture emerges. Let's bring it all together. We have looked at the speed, the scan, the silence, and the shadows. Now, as 3I Atlas recedes into the darkness, fading from even our most powerful telescopes, we must synthesize what we know. We must draw the line between what is possible and what is probable. The resulting picture is one in which radio observations provide a clearly dated and quantitatively defined negative result. We know that on December 18, 2025, in the 1 to 12 gigahertz range, 3I Atlas was silent down to the power of a cell phone. That is a hard data point. It is a constraint that any future theory about this object must satisfy. Simultaneously, this result underscores a fundamental limitation of our instruments. We can only find what we are looking for when we are looking for it. The universe is vast, and our window of attention is narrow. Against this backdrop, the more conservative interpretation remains dominant. According to NASA, the object posed no threat to Earth. It did not approach closer than about 1.8 astronomical units. It traveled through the solar system at speeds on the order of 200,000 kilometers per hour relative to the Sun. These numbers tell the story of a natural event, a gravitational kick from a dying star, or a chaotic interaction in a forming planetary system eons ago ejected this chunk of ice and rock. It drifted for millions, perhaps billions of years, alone in the void. It fell into our gravity well, sped up, heated up just enough to release a puff of gas, a cometary sigh, and is now leaving. It looks like an ordinary comet. It behaves like an ordinary comet, and it emits no detectable radio signals. For the vast majority of scientists, this is the conclusion. Case closed. It is a messenger from another star, yes, but a geological messenger, not a biological or technological one. It carries samples of the primordial soup of another system, not a greeting. And yet, the very fact of this silence, observed within such a narrow and fleeting window, does not completely close the question. It establishes that at the time and in the frequency range we examined, the object remained silent. It leaves that tiny sliver of what if that drives scientific curiosity.